and 30 years experience in engineering. Mark has been involved in materials research focused on high-temperature polymer matrix composite materials for aircraft engine structures. He dealt with materials and processing and strengthened the durability of these materials in service. Mark used CAE to drive designs of precision heated and unheated production tooling components, as well as for which he was granted patents related to that work. And he's also worked for a couple of small high-tech companies involved in impingement, heat transfer, and polymer processing. Please join me in welcoming Mark on the stage.
Thank you, Pavel. So this sounds like a big topic, but I'm going to try and, I was told I had 15 minutes to present multidisciplinary fatigue workflows, and that's quite a challenge. So I'm going to try and present it in a creative way, and I hope that I get some of the message across to you. So the multidisciplinary I'm talking about is using the tools in the Simulia portfolio. So that's Abacus for finite element analysis, Isight for process automation and design optimization, Tosca for non-parametric optimization, and Isight for fatigue. And I think the key takeaway is that many of you have what we call extended packaging. It's our new licensing system. And if you don't know if you have it, you should ask someone. You can ask your SR, you can ask your IT people. But if you have extended packaging, you have all of these tools that I'm going to talk about already. You just have to choose whether you want to use them or not. So the way I want to try and present this is I'm going to create a fictional couple. Their name are Andy and Laura. They're a retired couple from the Bay Area, and there they are. Andy and Laura love to travel to Flagstaff, Arizona, and there's their motorhome. They like to camp up there. Andy is 64 years old. He's in pretty good health, but he had an accident in 1975 when a control arm bushing failed, and that led to an osteoarthritic condition. But other than that, he's in pretty good health, and he still loves to ride his motorcycle. And they bring their motorcycle with them on their trips usually. So Laura is his wife. She's 62, also in good health. She did have some heart issues, but arterial stents helped to mitigate some of those issues. And Laura loves to go fly fishing, usually while Andy is out riding his motorcycle. So here's Andy and Laura. They're heading up to Flagstaff. They have to drive across California, through the Sierra Mountains, down the other side, then up into the mountains where Flagstaff is located. So Andy may be a little bit worried about having a control arm bushing in his motorhome, or multiple control arm bushings. But if he knew what happened behind the scenes at the manufacturer, hopefully they did a design process something like this. So this is a workflow that uses Abacus and Isight on the left side, and on the right it uses Abacus, Tosca Shape, and Isight. So basically the left loop uses optimization and our data matching functionality within Isight to actually match the desired load curves in 3 different directions for this bushing component. Once that is done, the bushing is actually optimized using Tosca shape optimization to make subtle changes to the surface to improve fatigue life. And then you go through this loop a couple of times, you end up satisfying both conditions. But I want to concentrate on the fatigue part of it because that's what this conference is really concentrating on. So a shape optimization, what you do is you have nodes on the surface, and you can move those nodes in and out a little bit and change the shape of that surface subject to constraints. So this bushing has to be stamped, so those bean-shaped holes have to have a stamping constraint on them. There's a symmetry constraint due to the shape of the bushing. There's certain areas, such as the outer surface and the inner core, which are frozen. You can't move the nodes there because the rubber is going to be bonded to steel in those areas. So what you do is Tosca will move those nodes in and out a little bit, subject to those constraints, and try and minimize fatigue damage. So Isight is tied into the loop with Abacus and Tosca. And the way it works out, if you watch this animation, you can see kind of the radius in that bean-shaped hole being changed a little bit. And the result is they were able to double the life of this component by just that subtle change in geometry. And this process took 12 iterations, and it cost 2 hours and 23 minutes on a single CPU. And this shows the fatigue results. On the left is before the shape optimization, on the right is after. They're slightly different scales, but they are very representative of the results. And the fatigue life was doubled. So we did talk about Isight, and I want to use Isight, which was used in this case for an optimization and data matching, to segue to talk about Isight for process automation. So if you remember, we said Andy has a hip implant. So we can imagine that whoever designed and manufactured that hip implant couldn't just design one, because different people have different heights, they have different angles involved in their anatomy, they may have to correct an offset. So there has to be a whole family of these hip implants, and it wouldn't be unusual to have 200 variants in a single product class. And in the old days, you would have to test every single one of those variants and show that it could meet fatigue life. So if you had 40 test machines, and say it took 12 days to run one cycle, it's going to take you at least 60 days to certify this product class. But if you could do this and in the virtual world and simulate the stress and strains and the fatigue life, and then take the worst case and test it on one machine, you could certify in less than 2 weeks. And of course, there are specifications out there from ISO and from ASTM that actually outline this process. So the way this was done is one of the major sizing parameters, which there were 8 of, was used for each of these DOEs, and then the other parameters were looped under that sizing parameter. So there was a total of 8 DOEs that were run in Isight. And then if you look at DOE 1 or any of the other ones, you'll see what the loop is. So basically, there's this data exchanger which gives you all the geometry parameters for the current design to be evaluated. That's sent to Abacus, which generates the geometry, meshes it, go through a specific mesh refinement in certain radii and other areas, and then the stress results are created in Abacus and sent to FE-Safe. And FE-Safe gives you a factor of strength on meeting the minimum life requirement, as well as gives you log life. And you can see the hot spots in those radii there on the hip implants. And keep in mind that if you're using Abacus in parallel in Isight, that you can get up to a 60% token reduction by using it embedded within Isight. And we do that to enable you to do these type of workflows without having to multiply your token pool too high. So the end result is, for instance, DOE 1, there were 24 variants. It was actually 23 because one was a non-considered variant. And for each variant, you get a fatigue life out, and then you can generate the minimal amount of data that you want to store, such as the geometry, the final refined mesh state, the mesos stress, and the fatigue life, and then you can use this for your reports to regulatory agencies or whatever. And interestingly, after this design was completed, this design workflow, the worst variant was taken and brought into Tosca shape again. And you can see, if you look at the hotspot diminishing, that radii was broadened out a little bit, and they were able to increase the fatigue life almost 5 times by doing the shape optimization. So probably what you would want to do at this point is parameterize that curvature of the new shape and then run the optimization again, and it takes less than 5 minutes per variation, so a couple of hours for this 200 hip implants. If you remember, we said that Laura had arterial stents. So sometimes Andy might be a little bit worried about her standing in fast-moving water, but due to the miracles of modern medicine, she feels fine. It's just a question of the fatigue life of those arterial stents. So hopefully they were designed with a process something like this one. So I'm not going to be able to go through the whole analysis, but if we start on the left with stress analysis, this is a workflow using Abacus. We're taking into account the bending, crimping, and insertion of the stent into the artery, the balloon expansion, and then the heartbeat fatigue load on it. And then the stent was optimized parametrically in Isight to increase fatigue life. And then finally, the fatigue life was improved again using shape optimization on this inner radius. And then at the end, a reliability analysis was done to take into account anatomic variation and its effect on fatigue life. And that's the part that I want to concentrate on. So we have some information that says that the thickness of the artery presents the largest source of uncertainty in the model. So what we do is we figure out what that variation could be, and we express it as an inner and outer radii mean plus standard deviation. And then we start going into Isight. We have two Isight workflows to look at. The first one is a structured DOE, where the different artery configurations are considered over a structured set of geometry. Abacus is run, FE-safe determines the fatigue life, and then the worst life is extracted. And what we do is we take that structured run and we build a response surface. And the reason we build a response surface is it's much more computationally efficient than trying to run Abacus hundreds of times. We then take that response surface and use it as an approximation for a Monte Carlo study under Isight. The Monte Carlo study generates potential inner and outer radii, and that leads to a distribution of FRF, or fatigue reserve factor, which is basically a safety factor on infinite life for that stent. So now we've taken into account the anatomical variation that we might expect for the fatigue life of the stent, and that makes Laura very happy. So we mentioned that Andy has a motorcycle and he likes to ride it. So he has a motorcycle, it's very fast, it's also very stable. Laura sometimes worries about his hip implant, but Andy's an experienced rider. And even though it's a fast motorcycle, it has really good braking. And that makes Andy happy. So everyone's happy. Now, hopefully that brake was optimized in a workflow, something like this. What we want to do is start with this standard brake geometry, and we're going to go to an optimized brake geometry. So I don't have time to go into detail here, but we start with the thermal optimization using Abacus. We take the thermal results and we go to Isight and do a parametric optimization for the size, number, and position of the cooling holes on the brake. And we're trying to balance braking surface area versus cooling. Once that optimization is done, we go to the second stage, which is structural. And we're looking at the inner disc now, the structural disc that's attached to the axle. And you can, if you see the animation, we're using topology optimization. So Tosca is removing elements where they're not critical. So the critical load path is kind of being defined here for the duty cycle that was specified for this braking situation. Once it's optimized topologically, we can smooth that data and then go into Tosca shape optimization again. And then we can do the same thing we did with the hip implant and the rubber bushing, just do a slight modification of the surface of the cutout areas subject to various manufacturing constraints. And once that's done, we can use FE-safe to verify the durability, and I'm just going to skip straight to the conclusion. The topology proposed design had hotspots. You can see the hotspots in some of these corners. And the factor of strength was less than 1, meaning it would not meet infinite life. But after optimizing it with shape optimization, the factor of strength was 1.4, or 40% safety factor for infinite life. And that's basically it. These are some of my colleagues who created these workflows. And if you're interested in any specific one of them, contact your sales rep and you can get a presentation of this.